All right, well, hey everybody. Today we're going to get into some more about interference and to a little bit of optics, things like that. So we're going to be talking about light. And one thing to say about light in terms of what we're not going to cover is that if we had, many more weeks of class, we could, like as in like if there wasn't any virus and then we had more weeks, we would probably cover lenses and optics, things like that. So not even in a normal class would we have time to cover those things, even though it's kind of interesting, especially if you get into photography, things like that. So today we're going to talk a little bit about that sort of a thing. We did talk about Snell's Law. Snell's Law is still very much fair game for the exam. And it's not hard to imagine how Snell's Law could be used with a curved piece of glass of some kind in order to create images and things like that. So that's all I'm really going to say about lenses. We'll talk briefly about lenses later on, but it's, again, don't expect all these like focal length questions on the exam, on the final exam or anything. So to talk about light goes back all the way to 1704. So after Newton figured out all the stuff about gravity that he figured out and invented calculus, the next thing he started doing was experiments on light to try to understand light. And so one of the experiments he did was he used a prism to break up light into the different colors. And Newton was convinced that light was made of particles. So that was nice for him because then it would fit into his framework of how gravity worked and things like that. And so he was very, very interested in this topic. And Einstein sort of envied him for his ability to be able to do both theoretical stuff and also be able to do experiments. And in many ways, this book, Optics, is the foundation for the field of experimental physics. And so Newton made a great contribution there as well. Now, Newton would not have called it particles. He would have called it corpuscles, but different names for the same thing. And the idea is that white light is made up of particles of all the different colors, and it's not until you put into a prism that their trajectories differ because of the different colors. And so to Newton, this reveals that light is made out of a particle. So not all of Newton's contemporaries agreed with him that light was made of particles. So there's a physicist named Hooke, so he came up with that formula for the restoring force of a spring. There's another physicist named Huygens who was also thinking about this, and they were very familiar with experiments that showed that light seems to be a wave, and we're going to talk about those experiments in just a minute. And later on I'll talk about how, at the end of the day, light has both the qualities of a particle and a wave. And so we're going to talk about that. Now, what does that mean? What's the difference between a particle and a wave? Well, this is a silly thing I found on the internet, in which basically depicts the scene in which if you have one opening and you're shooting a machine gun at that opening, because bullets are basically particles, they just go through that opening. And so if you look over here at the brick where the bullets are hitting, it's going to make this sort of a pattern. So this is a very particle-like thing to do. Whereas waves will diffract and interfere and do all sorts of interesting things, much more interesting than just sort of creating the outline here. And so if light does this, well then light is particles, but if light does something much more interesting, then it seems to mean that light is a wave. And so there's a nice demo here. I usually do this demo in Marion, but of course I can't. So I'm mostly going to talk over this guy and sort of explain what he's doing. So I hope you don't mind that.
What we have here is
let me mute his video real quick. Okay, so he's got a laser that is aimed at this. There's a bunch of different openings here, and so one of the openings is just a single slit, a single opening like you just saw, and then others of them are two slits together with different separations and things like that. And in a second, we're going to look at what pattern this makes on the far wall. So you can see that in just a second. And so we're going to find out whether light is made of particles or made of, or maybe it's a wave. And so this is a single slit. And again, if it was just the opening, you would only see this middle part, but in fact you see a little bit of light over here. If you look carefully, you can see light over here. Again, there's light over here. And again, if you look very, very carefully, you might be able to see light over here. So it's not just all in one spot. It's more extended than that, which is a very wave-like thing to do. Now in a minute, he's going to switch to the double slit, and the pattern is going to look similar but different, and what you'll find is that the overall outline is similar, but you see more dark spots in this pattern. And so that's from the double slit pattern. Yeah, so you see more. See, there's a dark spot here and a dark spot here. You still kind of have an overall thing. There's the central part that's bright, but you do see more dark spots. So we're going to talk about that in a little bit. But suffice it to say, if you have two slits, then if light really was a particle, you would just see the outline of those two things. But you don't see that. You see this very complicated pattern. And that's what tells us that light has qualities of a wave. So that's kind of the takeaway from this experiment. Let's see if I can get this. So there's a variety of different experiments that shows that light has the qualities of waves. So for example, this is an experiment where you take a laser and you shine it on an old school razor. So I use this. This is how I shave, for what it's worth. Excuse me. So there's a variety of experiments that show that light has the qualities of a wave. One of them is this one. So if you shine light on something that's opaque, like an old school razor, so this is just a thin piece of metal that can block the light. If you look very, very carefully, you'll notice that the light almost seems to bleed around the edges of this thing, right? Because if this was just blocking the light and the light was just particles and stopped the particles, then you wouldn't see these like edges. You wouldn't see these like, it would just be black here, right? You wouldn't see this edge here. Same sort of a thing with sunlight. So here's this sort of a pole that's in the way of the sun, you can kind of see the sun's rays kind of bleeding around it. So this phenomenon is called diffraction, and it's a very wave-like thing to do. Like if light was just particles, it would not do this. It would be stopped by this pole, and you would not see this sort of like bending around. Now it's important to say that yeah, so in Newton's day, I mean, they didn't have lasers, right? So this experiment is with a laser. So they didn't have lasers then, but they had sunlight and they had other ways of making light. And so Newton and his contemporaries were aware of the experiments that suggest that light has wave qualities to it, or wave properties. And if you look at even if you look at the shadows that the sun makes, you can see that the edges of those shadows are not perfectly sharp. And my understanding is that is also because of the wave nature of the light. I mean, the wave nature of the light it's very small. It's like 500 nanometers or something like that. But that's enough for it to sort of bend around it just a little bit for you to see what's happening. So especially with a sharp interface like we've been talking about. Now, this behavior of light is more apparent the longer the wavelength that you have. So the longer the wavelength of light, the more it behaves like a wave. And in a lecture or two, when we talk about the particle qualities, the particle properties of light, the experiments we'll be talking about have to do with light that is at shorter wavelengths. So for example, ultraviolet light and X-rays, those are much shorter wavelengths than just sunlight, for example. And so that it's easier to see the particle nature of light. We're going to talk about, we're going to continue to talk about the particle qualities and the wave qualities. You know, it seems to have the qualities of both. So now there's certain things that, there's certain experiments that Newton's contemporaries would not have been able to do, and that are easier to do with lasers. And the next one on the next page is one that's best done with a laser. And when I say laser, the reason lasers are useful is because they have one specific wavelength of light, whereas sunlight has a variety of wavelengths. And so so it's very helpful to be able to have a laser to do this sort of a thing. So if you take a laser and you put it through sort of this opening, this is a single slit, this is the kind of thing that we saw in that MIT video. There's sort of a central bright thing, there's a little dark spot, and then there's a brighter thing here and a brighter thing here. It was very hard to see in that video, but if you looked closely enough, you might be able to see this thing and then this thing there. Obviously the peak brightness is in the middle there. Again, this is not at all what you would get if light was a particle. You would just see some sort of opening. But the reason this is happening is because you're getting interference, and so basically the light is coming in, and it's sort of, when it goes through this opening, it's as if it's being emitted from each little spot. And so there's places where it constructively interferes and places where it destructively interferes. Again, particles would never do that. And so this is the pattern that you get. I don't want to derive this pattern, but I will tell you that once you get this pattern, the dark fringes go according to this formula. So this is a dark fringe, this is a dark fringe, this is a dark fringe. If you look carefully at the x-axis here, the x-axis is a little bit weird because it's pi a sine theta over lambda. And so when this is equal to pi or 2 pi or 3 pi, that's when you get a dark fringe. So I'm going to give you that formula. And A, by the way, is the size of the opening here, and lambda is the wavelength. Sometimes it's useful to convert this into y and L because there might be some distance between here and the pattern there. So this is the full formula for when you shine light through a single slit opening, you get something like this. And remember that x-axis of that plot was pi a sine theta over lambda. Well, this formula is what we are seeing here. This is what's plotted. If you want to plot this on your calculator, you can plot something like that, and that's what you'll get. And so when we're trying to figure out what the dark fringes are, we mainly just look at this sine function and say, all right, well, when is this sine function equal to 0? And those are the angles that produce the dark fringes, and that's what you'll be doing on the worksheet today. Now, because there's this relationship between theta and y and L, there's a triangle here, sometimes it's useful to simplify this formula. So it's, you can write out the sine function. Sine is opposite over hypotenuse. The hypotenuse here is this. Most of the time the distance to the plane is going to be much smaller than the size of the aperture, and so the square root of L squared plus A squared is often, you can just approximate that as L. So this is a perfectly valid way of writing it. And so again, in the worksheet, we'll be thinking about this formula and proving that this is the formula for the dark fringes from this intensity pattern. Okay? Now for double slit interference, it looks more like this. So now we have 2 openings, and so as a result, there's more opportunities for things to destructively interfere. And so as a result, there's more zeros, and so you can see these places where the intensity goes down to 0 many more times. You still get the same kind of outline, but there's many more what are called nodes in which the destructive interference takes the intensity down to 0. Again, this is a very strange thing for particles to be doing. If particles went through these openings, you would just see the 2 outlines here, but that's not at all what happens. It's a much more complex pattern, and we did see this in the video towards the end. I think there might have been only 3 bright things in here instead of like a dozen, but we did see that in the video. So to get this pattern, the formula for this, all of our dark spots still apply, but now there's many new dark spots, additional nodes. And so our new formula here is this, which this part should be familiar to you, but this part is new. So this part has to do with the width of those single slits, but this one has to do with the spacing between those 2 slits, d. So the spacing from the distance from this slit to that slit is d. And so, so you get zeros if the sine function here is equal to 0. But you also get zeros if this cosine function is equal to 0. So that's why there's so many more of these zeros. And so your job in the worksheet is to think about what angles would that be that you get additional nodes. And you might find these formulas useful because you've got, you usually have, there's some distance, there's some, distance to the wall, and there's some distance along the wall. So you can rewrite if you don't want to write the angles, you can rewrite it this way. So maybe not so helpful on the worksheet, but nevertheless this is true. All right, now we're going to talk about eyesight, and the next video is pretty interesting. So this is the first semester I've added this video, and I think you'll enjoy it. So let me go ahead and play that.
Vision is arguably the most compelling human sense. Words and stories and sounds allow us to imagine strange beasts and far-off worlds, but seeing makes us truly believe they exist. And that's why we place so much effort into correcting the optics of our eyes when they don't work, whether with glasses or contact lenses or surgery. But if you're in a pinch, bleary-eyed, or missing your glasses, there's a simple trick that will allow you to see clearly. Just make a tiny, tiny hole using your fingers, look through it, and the world will become clear again. This works no matter how blurry your vision is. Take off your glasses and give it a try. Amazing, right? But to explain this wizardry, we just need to remember how seeing works. Light travels outwards from a source, bounces off of objects in its path, travels into your eye and onto your retina, where it forms an image. If your eye had no lens, light from a single source would hit your retina in lots of places and result in a smeared out mess, which is exactly what happens when I take the lens off of my camera. A lens focuses that spread out light, corralling it into a crisp image on your retina, and after a little excitation of light-sensitive nerves and interpretation from your brain, you see. But wait, when we look at an object, the background and foreground are usually blurry, because a lens can only focus light coming from one distance away. If an object is too near or too far, its light will again be spread out on your retina, leaving you with a blur. Fortunately, muscles in our eyes allow us to accommodate by squeezing the lens, which changes its focal length so we can see at different distances, except when we can't, or when our lenses become damaged, in which case we need glasses. Unlike a lens, a pinhole or other small opening can focus light coming from any distance. Because it's such a small opening, it only allows light to come through in one place, and thus in only one direction from any particular source, so there's no blur, and everything is in focus. If you're familiar with photography, this is why using smaller and smaller apertures makes everything in your photo come into focus. Of course, small openings like pinholes and camera apertures create crisp images by blocking rather than focusing light, so the images are much darker, which is a major reason why we use lenses rather than pinholes for glasses, telescopes, and eyes. And yet, in a pinch, looking through a tiny hole made with your fingers can help you see. Now do you see why?
So I thought this was a pretty cool video and demonstrating the effect. The original camera, the world's first camera, was the Kodak camera, which it's laughable to me that this is how it works, but it was literally a box with a hole in it, and then there was photographic film on one side of that box, and that would take an image like this. And so the point of that hole is that this part of the image where the photographic plate is, if you think about it, the only thing that can add light to that plate is, is like up here plus or minus this and that. It's a very narrow range that can actually make it to this little spot on the photographic plate. And you can imagine how if you make this opening larger, well then it's sort of like a larger range, like maybe it's this and that. It's like a larger range from here to here, and then you might get a fuzzier image. And sure enough, that is what happens. Now, most of the time when we think about apertures and photography, we think more about the exposure rate, and the larger the aperture, the shorter the exposure rate should be. Otherwise, your image is going to be far too bright. But this is the basic idea. And so when you're using your finger to look at something, and I really do encourage you to try this. You actually can see more clearly by looking through a little tiny hole. So for example, if you lose your contact lens or something like that, you have nothing else to do. It actually can help you to read things that would otherwise be difficult to read. One fun part about when I watched that video is I remember watching the video and thinking to myself, like, yeah, but if I do the pinhole in front of my eye, why isn't the image upside down like this? Is sort of what I was thinking during the whole thing. Do you guys know why the image isn't upside down when you do this with your eye? It's because the image is upside down. I just blew your mind, but your brain knows better. Anyway, so this is how it works. And as I said, that there's trade-offs with having a larger and smaller hole in it. Now at nighttime, your eyes will dilate, as you probably have seen this happen at least once. And so that will sort of degrade the resolution of what you're seeing, but at nighttime, you mainly just want to get more light on your retinas so you can see things, and so you don't care that it's less finely resolved. If you do care about how finely resolved things are, which is what we're going to talk about in the next slide, there's a way to kind of take what we've been talking about and come up with some formulas for at best, your eyes can resolve these sorts of features. So if there was one tiny little thing in the distance, at best your eyes would be able to resolve that to some angle. So for example, let's compare single slits to circular openings. We've mostly been talking about single slits. And so cats and snakes and the Eye of Sauron all have single slit eyes. And so that's what we've mostly been talking about. And in a minute we'll talk about circular openings, so hold on tight for that. But these eyes are not so different than what we've been talking about, right? Especially, this case, right? So you can think of it the opposite sense of what if the light was going in the other way. We can use what we figured out and notice that if we had one thing that we're looking at, there's sort of an intrinsic size of that thing. And the size of the dark fringes, so this is, the angle of the dark fringe is like here, right? And so that's the angle of the dark fringe, and so the angular size of this whole thing is going to be twice that, right? So at best, your eyes will be able to see, objects according to sort of twice the size of the dark fringes. And we did a bunch of math to show that the dark fringes had to be something like this, where D is the diameter of, say, your pupils or something. Or, well, I guess D would be the diameter of the cat's eyes here, right? And so if lambda is small enough, and usually lambda is much smaller than the diameter that we're talking about. So later on we'll talk about 500 nanometers compared to a couple of millimeters. And so if that's small enough, well then you can approximate that with that. And so the best angle that you can resolve with cat eyes is the width of those eyes times 2 times the wavelength that you're considering. And so that would be the best angle that cat eyes would be able to resolve. Now, how does this work for circular openings? Well, this math doesn't apply because this is assuming a single slit. So when I showed you that slide earlier, there's a hole and there's some vertical thing to it. It's not a circle that the light is going through. But if there was a circle that light's going through, we'd be imaging things like this. There's a bunch of different math involved, but you end up with something somewhat similar to this case, which is instead of being twice the wavelength times the diameter of the slits, now you have 1.22 times the diameter of like the pupil. And so the math for this is not so fun to go through, but you can kind of see roughly what's involved and where this comes from. So I'm going to apply this equation real quick because there's some questions on the homework on how to do it. And so let's say that there's a car coming at you from far away, and you want to know how, at what distance, closer than what distance should your eyes be able to see two headlights as opposed to one headlight, right? So at some distance, these two things blur together like they do in this figure. And if it's closer to you, you can see them distinctly. If it's further than that, then they basically mush into one thing. But there's some, at some distance, you can resolve the two, right? And so we can use this to calculate what that distance would be. And so if we're talking about optical light, the middle of the optical spectrum is about 400 nanometers. So your eyes can see from something like 400 nanometers to maybe 700 nanometers. So in the middle of that is 500 nanometers, let's say. The diameters of your pupils, it changes depending on how light or dark it is. But roughly speaking, 4 millimeters isn't crazy. And then the distance between two headlights, maybe that's 1.5 meters, maybe 1 meter. And so we can do a calculation to try to figure this out. Now remember, it's very far away, so we can use small angle approximations. We say, all right, well, there's some resolving angle here, and we can calculate what that angle is, right? So because we know what the wavelength is, we know what the diameter of the pupil is, and then we can take this divided by that to get the distance, right? So this is in a small angle approximation, this would be true. Right? I could do the whole triangle. I could say, all right, well, there's some tangent theta thing going on. And what's, the opposite side of that triangle is the distance from the two headlights and things like that. But in the small angle approximation, it's just going to turn into this. And so the distance for which you should be able to closer in, you should be able to see both of those headlights, would be 1.5 meters divided by this. And so when you run this number, you get kind of a crazy number. So this is 10 kilometers. So it says that your eyes should be able to see both of those headlights if the car is closer than 10 kilometers from you. And if it's further than 10 kilometers, then you don't have a chance, which I have to say this number is quite a bit larger than I had guessed. But part of the reason why this number is so large is because it assumes that every other aspect of your eyes works perfectly, which is not even true of the world's best telescopes. They're not optically perfect by any means. They do the best that they can, and they calibrate them to an amazing degree. So in reality, this is sort of overly optimistic for how good your eyes are. But at least in terms of the physics, there's just simply no way that your eyes would be able to resolve two headlights further than 10 kilometers away, which maybe we already knew. We can't see things so well 10 kilometers away, but now we have physics to back it up. So anyway, hopefully this helps you with the homework. Send me an email if you have any questions, things like that. Let me talk about the worksheet real quick. The worksheet can be a little bit tricky, but here again is our pattern from when you shine light into one of these slits. And I don't expect you to come up with this formula, but I expect you to be able to use this formula to figure out where all these dark fringes are, and also to think about the bright fringes. So, this is a bright fringe, this is a bright fringe, this is a bright fringe. And how do we stare at this formula to figure out when those bright fringes are? And so there's just some basic questions about, like, if you had a sine function, when is that going to be 1? When is it going to be 0? And then you also, the thing about this is you have to think carefully about sort of, for each integer m, it might seem obvious whether a thing is a dark fringe or a bright fringe, but this pattern turns out to be very tricky. And the reason this pattern turns out to be kind of weird has to do with the fact that, you'd think that theta equals 0 would give you a 0 on this scale, right? Because if theta equals 0, that means the sine theta here is 0, and sine of 0 is 0. So you'd think that the intensity would be 0, but the thing is that you're dividing by this thing as well. And so this worksheet, that's the clever twist in this worksheet, is trying to figure out whether, for example, m equals 0 is a bright fringe or a dark fringe. And if you look closely at the diagram, it's pretty clear that it's a bright fringe. So there's some twists and turns of this in this worksheet. So I encourage you, I just want to give you a heads up that you really have to think carefully about what's the m and the 1 and the 2 and things like that. But at the end of the day, you could plot this up as something like, you know, sine x over x, for example. And when you do that, you'll get this pattern. But the reason you get this pattern is because you're dividing by x when it gets small. So anyway, just a heads up. And so go ahead and complete that worksheet and submit it to me, and I'll take a look and we'll talk. So all right, well, thanks for watching. See you guys later.